Hello everybody. In this lesson we're going to look at sine and cosine graphs. This is something you've had an introduction to before, so we will review the basic features of each graph. We'll revisit transformations and how they apply to these curves. During the course of the lesson we'll talk about what we mean by period and amplitude. And we'll do a couple of examples where we sketch a sine graph and a cosine graph. So I'll just get you to do a sketch of sine x, cosine x, just on your piece of paper. Pause the video, include as many features of each graph as you can. So let's have a quick look over these two graphs. Sine x importantly starts at the origin. It has a period of 2 pi. It goes through a 0, then a maximum, then another 0, reaches a minimum, and then a 0, then it starts all over again. Cosine graph, exactly the same shape. But the graph starts with its maximum on the y-axis, so it's going to go through the point 0, 1. It reaches its minimum halfway through the period at x equals pi, and completes one period by the time it gets to x equals 2 pi, and y gets back to 1. So these are the basic features of the sine graph and the cosine graph. We are going to visit tan graph in another video, another lesson. So let's talk about the sine graph in particular, and we'll talk about how the transformations relate to this graph. The thing about sine and cosine graphs is that the translations, or the transformations, are the same for each graph. So we will be able to translate graphs. So some sort of constant added onto the graph shifts the graph up a certain number of units, so we can have a vertical translation. We will have horizontal translations, just like we have with any other function. If we replace x with x plus something or x minus something, we see a translation to the left or right. An important transformation for these types of graphs is a dilation from the x-axis. And obviously you can see how the graph reaches a higher maximum, a lower minimum, but passes through the x-axis at exactly the same points. And we're just multiplying that function by some constant. Another important transformation of these graphs is when they're dilated from the y-axis. So they stretch away from or towards the y-axis. It changes the length of the wave. And this type of dilation happens when we give x a coefficient in the function, so f of nx. And of course we can have reflections in either axis. So the diagram here shows us when we have negative f of x, we have a reflection in the x-axis. The curve sort of flips around the x-axis. If we have f of negative x, so if we swap x with negative x in the function, we see a reflection in the y-axis. So it's the reflection in the x-axis that's shown in this diagram. With all of the sine and cosine graphs that we have, or we look at, we will often refer to the amplitude. So what you can see in this diagram here is sort of an imaginary line. It's a horizontal line, so that the curve oscillates exactly the same distance above and that same distance below that imaginary line. It's the distance between that line and the maximum, or between the minimum and that line, that we refer to as the amplitude of that curve, of that wave, whether it's sine or cosine. When we're talking about the length of the wave, mathematically we're referring to something that we call the period of the wave. So you can see here the graph is sort of starting on the y-axis at this imaginary horizontal line. It increases and then decreases and comes back to the start before it begins another cycle. It's that length of time or that angle of revolution that we would call the period. We have a formula for the period. The formula of sine x, the period of sine x is 2 pi between the origin and when it starts again. So if we are dilating that from the y-axis, it's got something to do with that constant of dilation. So if our coefficient of x is n, you might remember that the dilation, the factor of dilation from the y-axis is 1 over n. In other words, we can take the original period 2 pi, divide that by n, and that will give us the new period of the function. This is just the same two quantities, the amplitude and the period, shown on a different graph, just to highlight the features of the amplitude and the period. So we can see this imaginary horizontal line, the curve oscillates above and below that line. It's this distance here that we refer to as the amplitude, and this distance or angle of revolution or period of time we refer to as the period of the graph. So now that we've talked about amplitude and period, or the different types of transformations that we recognise when we look at graphs, let's have a look at sketching a function. We're going to sketch a sine graph first. So we've got the equation for y equals 3 sine 2x plus 1. I'm going to relate that to a function of x called sine of x, because I'm using that function in the equation we're graphing. So our equation could be stated in terms of f of x. So we've got a coefficient of 3, we've swapped x with 2x, we're adding 1 to f of x, so that our equation can be thought of as 3 times the function of 2x plus 1. This form of the equation sort of highlights the transformations that we can use for the sketch. So we've got that dilation by a factor of 3 from the x-axis. We've got that dilation from the y-axis by a factor of 1 over 2, or a half. And we've got a translation up 1 unit. So what we can see here before we do the transformations is the graph of sine x. And you might just see here, I've just made a faint line, that imaginary horizontal line, and the original period of sine x has been halved. So I'm imagining a curve that is completed in half as much time. And we've also got a dilation by a factor of 3. That's going to give us the distance between that line and the maximum, or that line and the minimum. So if my translation is positive 1, that imaginary line is going to be 1 unit above the x-axis. I can see that my dilation is going to be 3 units above and below that line. Putting those pieces together, I can sketch a rough curve. That's just one period. You're going to find in the exercises that we do that you might need to complete more than one period for a sketch. And from this we can see some quantities like the amplitude is 3. That comes straight from the function itself. That value there is our amplitude. Our period, which is 2 pi over n, is 2 pi over 2, which is equal to pi. And the range of the graph, let's refer to the range. Our minimum value is y equals -2. The maximum value of y is 4. So our range is from 2 to 4 inclusive. Other details might be required, especially in an exam situation. You might be required to show x-intercepts and coordinates of endpoints as well. For this lesson, we're just looking at the transformations of the curve. Now let's look at a cosine curve. So we're going to base our curve on f of x equals cosine x. We can see that we've got -2 as our coefficient of the function. We've swapped x with x minus pi on 4. So we're looking at something that has a reflection in the x-axis because of the negative, something that's dilated from the axis by a factor of 2. It's going to stretch the curve, the cosine curve. And because of the x minus 4, our graph of cosine x is going to be translated to the right, pi on 4 units. So here's our original graph of f of x, our cosine x curve. What you'll see here is I've made a mark. I'm looking for the points where the curve is going to cross the x-axis. I'll have a dilation from the x-axis and a reflection, but they're not going to affect the zeros of the function. What will affect the zeros is this translation. So you can see I've moved that 0 to the right, pi on 4 units. There's pi on 2, pi on 4 is halfway between that. So for each 0, we're going to skip across pi on 4 units. And taking into account the dilation, the curve is now going to oscillate between -2 and +2, and it is also reflected. So I've marked points where the minimum and the maximum and the next minimum will occur, and that will enable me to draw a rough curve for the function, for the equation. In this case, we've got an amplitude of 2. We've got a period of 2 pi, and the range is from -2 to 2. Just a word about rearranging expressions, particularly when we are looking for the transformations that we need to sketch a curve. The way that this curve is written, 4x plus pi over 3, that would be a translation to the left, pi on 3 units, followed by a dilation from the y-axis. It's important that we get those two transformations in that order. In that form, it's actually very difficult to see the translation in the final sketch. If we take the 4 out as a factor, what we end up with is a rearranged expression. In this case, we would dilate from the y-axis first, and then we would translate by pi over 12 units after that. I find that this is an easier way to sketch a graph when I've got a dilation from the y-axis and a horizontal translation at the same time. So just be aware that you may have to rearrange, or you may need to rearrange to understand the transformations that are occurring. A quick review. We're at the end of this lesson. We've reviewed the basic features of sine and cosine. Tan is coming later. We've talked about the different transformations and how we use those to help us sketch a curve. We've defined period and amplitude when we're looking at a graph. We have a formula for the period of the curve, and we've done a couple of examples where we've sketched a graph of a sine curve and a cosine that has gone through a number of transformations. If you could please write down any questions that you have that you want to bring to class, and as usual, complete the Google form to log your attendance and to check your understanding. Thanks very much.